Time travel used to be a taboo, relegated to the realm of science fiction. But a closet fraternity fell in love with this notion.
That's our dirty little secret. We physicists write articles on time travel, but we don't say time machines. We use a code word.
By day, illustrious scientists proved their mettle. By night, imaginations ran wild.
There was a young lady named Bright
who could travel much faster than light.
She set off one day in a relative way
and came back the previous night.
Their quest to build a time machine is about to come of age. Ever since Ron Mallett was a boy, he has harbored a dream of building a time machine. Today, he is Professor of Physics at the University of Connecticut and ready to share his secret with the world.
It's really such a powerful feeling to know that we're actually being able to manipulate space and time. And it's exciting because this shows that we may be able to control time, and that means that ultimately we may be able to control our destiny in a way that mankind never has been able to before.
Mallett's motivation began when his father died suddenly of a heart attack. Just 10 years old at the time and totally devastated, Mallett made a pledge.
If I could build a time machine, then I could go back and see him again and maybe save his life.
For almost half a century, and like many other scientists, he has conducted his research in closed laboratories.
It's only been since my own breakthrough at the end of the 20th century that I finally allowed myself to come out of the time travel closet, so to speak.
If he's right, the 21st century will see time travel make the leap from theory to reality.
It's refreshing now that in the 21st century we can explore this openly without looking over your shoulder like, when the guys in white coats are going to come and, grab us because we're talking about time travel.
Like all would-be time travelers, Ron Mallett had to find a way to understand time before he could attempt to travel through it. Leading theoretical physicist Michio Kaku has spent a career analyzing time. He believes a working time machine is inevitable. When we look up at the sun, we're actually seeing how the sun shone 8 minutes ago. Because it takes 8 minutes for the sun's light to travel the 148 million kilometers to reach Earth. So we're seeing into the sun's past. Kaku believes that to master time travel, we need to understand time itself. He starts by correcting 3 important misconceptions.
The first misconception about time is that there's a universal now. That if it's 12 o'clock here, it must be 12 o'clock on the moon, and by golly, it must be 12 o'clock throughout the entire universe. Actually, in reality, it is impossible to synchronize your watches throughout the universe.
This is because of misconception number 2. Many people believe that time passes at a constant rate.
People also believe that time ticks uniformly throughout the universe. Actually, that's not true. You can show that in outer space, a clock actually ticks slower than on the Earth.
In fact, our satellite navigation systems only work because the US military made corrective adjustments to the satellite clocks every single day. Time is not absolute. It ticks at different rates in different places. The time traveler must cast aside any notion of mechanical time. And embrace the idea of time as a dimension. Misconception number 3.
Most people assume that we live in a three-dimensional world. Actually, we live in a four-dimensional world, 3 dimensions of space and 1 dimension of time.
Thinking of time as a dimension might not come naturally to us, but Kaku has a way of helping us. Computer games.
What is so fascinating about Pac-Man is that Pac-Man lives in 2 dimensions. He can only go forward, backward, left, right, but the concept of up is totally alien. They cannot visualize the concept of up. They live in a flatland. Now, we also live in a 3-dimensional world. We go forward, backward, left, right, up, down, but we are incapable of visualizing a higher dimension, a 4th dimension. That requires a leap of logic that our brain simply cannot comprehend. Okay, I need to go to 5th Avenue and 33rd Street.
Just like Pac-Man, we use a 2-dimensional map to find a place on Earth. But unlike Pac-Man, we can leave the 2D flat world and go up into the 3rd dimensions of height. We also live in the 4th dimension of time. An appointment in our world might be in a building on a map and a floor in the building, but also at an agreed time. In fact, the 4th dimension of time is so interwoven with the other 3 dimensions of space that physicists now call the 4 dimensions together by one name: space-time.
We now believe that space and time are not invisible. They're actually a fabric that can be stretched, pulled, and perhaps even wrapped up into knots. If so, then perhaps the dream of time travel is not as preposterous as it sounds.
To build a time machine, we must find a way to manipulate this space-time fabric. Many scientists believe that it's this manipulation that will make time travel not only possible, but inevitable. We know how to change the speed we move as we rush along a busy sidewalk, but changing the rate we move through time is much more complicated. Most of us move forward in time at a rate of 1 second per second, but there are already time travelers among us.
Go for landing, over. Roger, understand. Go for landing. 3,000.
Astronauts on board the International Space Station have time traveled into the future. But how have they managed to do this? Space stations orbit the Earth at more than 27,000 kilometers per hour. Men and women have lived on them for more than 700 days. Upon their return, the astronauts had traveled a fraction of a second into the future. Their primary method? Speed. A spaceship is a time machine. The speed it travels at is slowing down time for the people on board. To demonstrate how motion can affect time, we must first appreciate that the speed of light acts as a cosmic speed limit. Nothing travels faster than it. This is a pulse laser. It measures one of the few absolute values in nature: the speed of light through empty space.
The beam comes through this series of lenses and mirrors. If we move that mirror back about a foot, then the light has to travel a further distance. And if I check this oscilloscope here, it tells me the extra time that the light has taken to cover this distance. So if we know the distance accurately and the time accurately, we can calculate the speed of light.
That speed is 300,000 kilometers per second. And experiments prove that this figure is constant across the universe. Because it never changes, it means that time can be manipulated. Physicist Jim Al-Khalili demonstrates that time can be stretched or squeezed. He uses a theoretical light clock located on the dashboard of his car. This device bounces a beam of light up and down inside the car, which is traveling close to the speed of light. The different way in which observers inside and outside of the car view this light beam demonstrates that they experience time at a different rate.
For me, travelling with the clock inside the car, I always see the light beam moving vertically straight up and down.
If Al-Khalili's twin brother watches from the roadside, he would see the light beam follow a different path. Combine this horizontal movement of the car with the vertical pulse of the light clock, and one thing results.
For me, standing watching the car go by, I see the light beam travel diagonally.
The distance light covers is greater for the viewer outside the car. But crucially, the speed of light is the same for both. Time equals distance divided by speed, so the time passed is less for the person who is travelling in the car. Time actually passes more slowly for the person who's travelling at speed. Scientists call this time dilation. Geneva, Switzerland. This is CERN, the European Organization for Nuclear Research, home of the world's largest particle accelerator. Scientists from 85 different nations study the subatomic world to understand how the universe works. At this space-age facility, they have been carrying out time travel experiments for more than 40 years. A useful time travel particle is the muon. Muons are high-energy particles produced by cosmic rays, which constantly bombard the Earth's atmosphere. Muons live for only about 1/1,000,000th of a second. Here in CERN, scientists use speed to make these subatomic particles live longer, thereby turning them into time travelers. Giant accelerators like this one at CERN push the muons to velocities approaching the speed of light.
If we have a muon traveling in a ring at close to the speed of light, its lifetime is prolonged. That means that the clock, which the muon is ticking slowly, slowly, slowly. So when the muon comes back, it has only gone through tick-tack, 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 while we have gone tick-tack, 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 tick-tack. So in a sense, the muon is coming to our future, because only 1 second has elapsed for the muon, 20 seconds have elapsed for us.
Scientists enable muons to time travel into the future by slowing down the rate of time for muon. There is, however, a catch, which is the major roadblock to using speed to build a time machine. Any mass has an associated energy. As an object gains energy by moving at speed, its mass actually increases. The metal balls on this office toy weigh more when they are moving than when they are at rest. But because they are moving slowly, the increase in mass is very small. If they were moving at close to the speed of light, the increase in mass would be immense. In fact, a subatomic particle whizzing around the CERN accelerator close to the speed of light can weigh more than 7,000 times its weight at rest. As the particles get heavier, scientists at CERN must provide more and more energy to keep them moving.
As you increase the energy of the particle, you get closer to the speed of light. And then you double the energy and you get a little closer. And then you double the energy and you get a little closer. But you never go beyond. In order to reach the speed of light, you would need an infinite energy, which we happen not to have available.
If energy is the stumbling block of subatomic time travel, then imagine the scale of the problem for a human-sized time machine.
The main problem with using speed to time travel is that we can't move an object anywhere near to the speed of light. It would take all the Earth's energy resources just to push our rocket to a tiny fraction of the speed of light. But you wouldn't notice any difference unless you got very close to the speed of light itself. We simply don't have enough energy.
And there's another problem. Using speed to build a time machine is a one-way journey into the future. Traveling close to the speed of light will enable time travel to the future, but the time traveler has not mastered time. He has merely slowed down his own rate of time and fast-forwarded himself through time. He wouldn't be able to come back to tell his tale. There is, however, another way to build a time machine. Gravity. Many of us think of gravity as simply a force that keeps us on Earth. But scientists here at Manchester University in England view it in a totally different way. For the time traveller, gravity is evidence of how mass bends or distorts the space-time fabric. Professor Brian Cox is an expert on gravity and on how it interacts with space-time.
Space-time's not just, up there, it's here, it's in front of me and it's inside me. And I bend and curve it a little bit. I produce a little bit of gravitational force. But of course I'm very light, so when I move I don't curve it very much. But something the size of a star or a galaxy or a black hole warps and curves the space-time a huge amount.
The greater the mass of the object, the greater the impact or dent on the space-time fabric. This isn't just in theory, here's the evidence. These Hubble telescope images show what is happening to light as it travels through space. As light passes a galaxy, its path bends. By examining how light bends as it travels, we can prove that mass is bending space-time. This experiment replicates this phenomenon in a lab. It's a mini-universe, and it shows how light travels across space-time. In flat space-time, a light beam follows a straight line. But there is evidence that light is bending as it travels through the universe. The path it follows must also be bending, and that path is space-time itself.
Billions of stars are bending the space-time, acting like a lens. So a lens curves light, and if you bend the space-time, the light will curve. So you get the image of the galaxy in the middle, but then you get these really distinctive rings around. And that's strong evidence, overwhelming evidence, that mass bends space-time.
This warping of space-time will help us to build our time machine. When gravity bends space-time, it has a very real effect on how time passes. Here on Earth we might not feel it, but time runs slower on the ground floor compared to at the top of a skyscraper.
The closer I am to the Earth, the more curved the space-time, the stronger the gravity, and the slower time ticks. Whereas here, space-time's a little bit less curved, gravity's weaker, and so time ticks faster. Now, it's a really tiny effect. If I was to stand at the top of this building for 100 years, then my watch would be 50 millionths of a second faster than somebody's watch down on the ground. So in a sense, the Earth is a time machine.
Take this into space and the effect is even greater.
Yeah, I'd like to go to the university. It's M199QL. The fact that time passes at a different rate in orbit a long way from the Earth than it does at the surface of the Earth is really important for GPS or sat-nav, because that works by having synchronized clocks on the ground and in the satellites. And because the satellites are in a weaker gravitational field, time is passing more quickly. And actually, there's a time difference of 50 microseconds a day, which is 50,000 feet a day. So if you didn't correct for that and didn't take account of the fact that time passes at different rates, satellite navigation wouldn't work.
Earth's gravity and consequent warping of space-time isn't extreme enough to help a time traveller journey into the past. But there are places in the universe where gravity dramatically distorts space-time.
Most of space-time is nearly flat. It is only in black holes that it is strongly warped.
Professor Stephen Hawking is renowned as a world expert on black holes. Back in the 1970s, his groundbreaking research illuminated the then theoretical black hole. The gravitational pull of a black hole stretches and warps space-time around it to an incredibly deep cone-shaped hole. Because the gravity of the black hole is so intense, it drastically slows down time. Physicists like Hawking are fascinated by what a black hole does to time, but there is a catch. The black hole has a boundary called the event horizon, which leads down to the densest point, the singularity. Not good news for the time traveller.
In a black hole, you would be bound to hit a singularity and be crushed out of existence.
This is the Chandra X-ray Observatory. It's located 200 times higher than the Hubble telescope, and it provides scientists with new data on black holes.
Thank you, sir.
The mirrors on board this satellite are the smoothest mirrors ever constructed. Chandra sends back X-ray images 10 times sharper than the best previous X-ray telescope.
82 EPS.
That's the equivalent of reading a stop sign from 19 kilometers away. When scientists analyzed X-ray images of supermassive black holes, they discovered that they were spinning at close to the speed of light. This causes the space-time fabric to be dragged around. Scientists call this frame dragging. Space-time becomes so distorted that it forms an almost complete circle. Confirmation that black holes rotate was music to the ears of anyone interested in time travel. The time traveller was just about to strike gold.
I think I and other people that are working on this would feel like pioneers in the field of time travel.
So convinced is God that time travel will one day be possible, he'd volunteer himself as a guinea pig.
I guess it'd be worth the risk.
Gart is one of the few physicists in the world who claims to have found a solution to voyaging back in time. He figured that the secret to building a man-made time machine was to take inspiration from the universe and then copy it.
One place to look for a naturally occurring time machine would be in the center of a rapidly rotating black hole.
What intrigues Gart is how the rotating black hole warps space-time around it. Gart is a professor of astrophysics here at Princeton University. He searched the universe to find anything that could warp space-time as much as a rotating black hole. What he found led him to make a bold and ambitious hypothesis, which is based on something that is still theoretical. It's called a cosmic string.
Cosmic strings are thin threads of energy that are left over after the Big Bang.
Despite being no wider than an atom, cosmic strings have colossal density. A string just 1 meter long would exert more gravity than the Earth. Immense gravity warps space-time. With his eye on time travel, that means one thing for Richard Gott.
Please enjoy your meal.
Thank you very much. I found out that because of the warping that the strings do in space-time, that if two strings, infinite strings, were passing each other at high speed like this, you could use them to make a time machine.
The fast-moving strings warp space-time as they pass, so that they bend it down into a wedge shape. Normally, a spaceship would have to take the longer route across space-time. But the time traveler can now take the shortcut. By outrunning a light beam, he can travel back in time. If this car were a huge spaceship, and God could find two cosmic strings, he could return before he departs. The space-time around the two moving cosmic strings is so twisted that God can circle the strings and come back before he sets off. Here's how. Cosmic strings bend space-time and provide a shortcut. By journeying around the strings, God travels faster than light does across normal space-time.
You can't build a rocket that goes faster than the speed of light, but with curved space-time, you can take a shortcut and beat the light beam and theoretically make a time machine in principle.
The path of time is no longer linear. Instead, it forms something like a circle. There is, however, a small hitch. Cosmic strings are not only purely hypothetical, they're also elusive.
We wouldn't expect you to be so lucky as to find two infinite cosmic strings passing each other at the speed required to make a time machine.
God navigates this strings problem with a hypothetical alternative. Cosmic loops. They too may sound far-fetched, but the skeptics could find no fault in God's theory.
Well, it certainly created a hubbub because many skeptical people might wonder whether you could actually do such a thing, but here was an exact solution of Einstein's field equations that allowed time travel into the past.
Richard Gott's time machine does, however, have a weak link. He discovered that at the very moment he warped space-time enough to form a circle, the whole region would fall inside a black hole.
And that's not good because a black hole, well, that's a hotel where you check in, but you don't check out. So it looks like the time travel region would be trapped inside a rotating black hole.
Even if the prospect of being crushed out of existence doesn't deter the time traveler, God's time machine has another limitation.
The string loop solution, if you wanted to go back in the past a year, it would take a mass of about half the mass of our galaxy. You'd have to manipulate a mass that large. So you'd have to be one of these galactic civilizations that had the energy resources of the entire galaxy at your command. So this is well above the current NASA budget.
It appears that a cosmic string time machine is a project for the future. Timescale, however, does not deter the time travel enthusiast. And God's theories encourage others to search the universe for naturally occurring time machines. In fact, as soon as physicists began to view space-time as a terrain, they started to search for ways to leap across or tunnel through it.
The best way to travel in time is to use some sort of shortcut between 2 points in space. On Earth, we're familiar with bridges and tunnels that create shortcuts. We need to do something like that in space, and then we could turn it into a time machine.
Professor Paul Davies has analysed all current theories of time travel. He's convinced that the strongest theoretical structure is something called a wormhole. Gravity warps the space-time fabric, and those interested in time travel claim that if this warping is enough, the fabric can bend back on itself. The wormhole is a connection between two regions of curved four-dimensional space-time. It has two mouths and a throat. So the time traveller could travel through the wormhole faster than it would take for light to travel across space-time.
Imagine that this sheet of paper here is part of space. We know space can be curved, and we can imagine it being curved right around like this, so it can connect up with itself in two different ways. The long way, around like that, and the shortcut through the tunnel that connects the two ends of the paper here.
In fact, the architecture of the wormhole has a logic we are already familiar with today.
This is a great example of a wormhole. You could go down in the elevator, across the street, and up in the elevator the other side, or you could take the shortcut through the bridge. That's exactly the same with a wormhole in space.
Like many in the time travel fraternity, Davis isn't deterred by the fact that scientists have yet to find a wormhole.
When I was a student, people talked about black holes, but nobody knew if they were really out there. Now we know black holes are for real. Well, we also talked about wormholes decades ago. Are they out there too?
And it's this that scientists in Europe hope to find out. Geneva, Switzerland is home to CERN, the European Organization for Nuclear Research. According to the scientists who work here, a new epoch of physics is about to begin. This is the world's largest particle accelerator, the Large Hadron Collider. Buried deep under the ground of Geneva, this 27-kilometer tubular ring will smash atoms together at close to the speed of light to recreate the conditions immediately after the Big Bang. When the subatomic particles smash together, they will produce tiny fireballs of primordial energy. Scientists hope this might shine a light on what the universe was like at its birth and illuminate elusive subjects such as dark matter, extra dimensions, and maybe even wormholes.
It's a very long shot, but we hope to be able to investigate whether we can actually create little black holes and little wormholes and little time loops.
Today, engineers lower one of the last pieces into place. The world waits with bated breath to see what this accelerator might reveal.
We're going to a land that has never been explored, and we might find these things if we're lucky.
Teams of scientists from all over the world will analyze the data from the accelerator and perhaps reveal, once and for all, whether wormholes can graduate from fantasy to reality. Some time travel enthusiasts believe that time travel to the past will be achieved not by us, but by a super advanced civilization. People with galactic power at their fingertips. One American scientist, however, is convinced he has the answer to traveling back in time, and he's got the evidence to prove it. Today, Professor of Physics at the University of Connecticut, Ron Mallett, thinks he's on the verge of traveling back in time.
Before, we felt like we were prisoners of time. Now, with time travel, we may be able to actually really know what's going to be happening and be able to do something about the past.
What makes Mallet different is that he doesn't take a purely theoretical approach to journeying through the fourth dimension. This maverick inventor thinks the age of time travel is now.
Because of the fact that, the progress we made with space travel in the 20th century, and I think that people now have this notion that anything is possible. The new frontier in a lot of people's mind is time travel. The early work of my colleagues that really inspired me was the work that had been done in rotating black holes, in wormholes, and in cosmic strings. All of these things lead to the possibility of time travel into the past. What I was interested in was a mechanism, something that could be used as a device that was different.
The common theme that unites rotating black holes, wormholes, and cosmic strings is gravity. Mallet searched to find a new way to harness gravity in order to time travel. Though light has no mass, it does have energy. Mallet was convinced that he had to take an unorthodox step to build his time machine.
And I found that light could be used to control gravity. And since gravity controls time, then that meant that I could use light to control time. And that's the basis of my inspiration and my theory.
Mallet guarded his ideas. Before announcing his theory, he had to make sure it had substance. He wanted to find a way to replicate the frame dragging of a black hole in order to twist space-time around into a loop. The answer was staring him in the face.
And I thought, wait a minute, if I can create the circulating beam of light, then this circulating beam of light can lead to a twisting of space. Should lead to a twisting of space. And if it does lead to a twisting of space, then it should also lead to a twisting of time.
For months, Mallet worked on his equations. He checked and double-checked the figures until he was ready to unveil his ideas to the world. While cosmic strings and wormholes would require an advanced super-civilization with the power of the galaxy at their fingertips, Mallet claims his time machine could be built not in the future, but today.
What you're seeing are four intersecting laser beams that are forming a square in which the light is circulating around, and the space is being dragged around by that. And in addition to the twisting of space, eventually in a real model, you'll have a twisting of time as well.
This is a model of Mallet's time machine. According to his theory, the laser beams will create enough gravity to replicate the frame dragging of a rotating black hole. Some claim this theory is off the wall, but Mallet insists his machine could create a minute time loop.
The real size of the real device, however, is going to be only about the width of a human hair, and rather than just having 7 lasers like this model, there'll be 10,000.
Mallet is now ready to step from model to time machine. The time traveler in his minute machine will be a subatomic particle.
Think if we could warn ourselves of future catastrophes. We don't need to send someone back. If we could just send information back, or if we could send back scientific information, medical information. I mean, think about that. Think about if we could send back a cure for AIDS, a cure for cancer. That's more significant than sending people back.
The boy who dreamed of traveling back in time to save his father's life might be on the verge of building a time machine. But Mallet, the physicist, now accepts he'll never be reunited with his father. Time travel to the past will only begin the moment his machine is switched on. Only time will tell if Mallet's machine is successful. But creating a machine able to travel into the past would pose a dilemma which many have struggled over for decades. No matter how attractive rewriting history might seem, any change would have consequences. If the time traveler alters the past, how would that affect the present?
that would lead to paradoxes, like if you killed your grandfather before your father was conceived.
For many, time travel to the past is simply too big a leap of faith.
We all are traveling to the future, whether we like it or not. We can fast forward by traveling near the speed of light, but the difficulty is to come back again. I haven't met anyone from the future.
But others find a solution to this argument: parallel universes. This truly does sound like science fiction, yet the evidence speaks for itself.
Common sense says that if I have tiny little billiard balls and I shoot them through a slit, I should get one big billiard ball hitting the screen over there. But here's a laser beam made out of individual particles of light, photons. When I shoot photons through a slit, lo and behold, look at this. This is the money shot. Instead of one big dot, we see multiple dots, as if the photon were many places at the same time.
Everything in the universe is made from subatomic particles. If photons can be in two places at once, could we?
We physicists now believe that in some sense the universe itself split into two universes. In one universe, the photon went to the right. In another universe, the photon went to the left. So in other words, there could be an infinite number of parallel universes, each one splitting off from the other ones. When I was a graduate student, I almost fell off my chair, realizing that perhaps not only electrons being two places at the same time, perhaps I am two places at the same time. Now, of course, I felt real. I felt as if I was just one person. But then I began to realize that perhaps my own body was splitting into multiple universes all the time.
In the parallel universe view, our universe is like a playing card in a deck of many. Not universe, but a multiverse. We coexist, and we could visit these parallel universes through time travel.
Multiple universes is perhaps the cleanest, simplest way to resolve all the time travel paradoxes. There are no paradoxes at all if you believe in the many worlds theory.
According to this theory, our view of history is out of date. Our logic told us that events were linear. They go by like stations: World War II, the atomic bomb, the first man on the moon. But in the parallel universe view, our universe is one of many in a giant switching yard. The time traveler simply jumps tracks.
Every time you go into a time machine, in some sense, you're monkeying with somebody else's past.
Time travel theories may sound far-fetched. Yet for the last century, pioneers have pushed the boundaries, turning science fiction into reality. They have blended imagination with knowledge to prove once and for all that time travel will happen. We may have only journeyed a fraction of a second into the future, but the time travel pioneers continue undeterred, driven by the knowledge that every epic adventure begins with a single step.